All right, I'm gonna throw. Oh, by the way, it's Ripley. Welcome back. We're in chapter 11. This is the last day. Woohoo! Hope you've had a good time. Kind of in summation, I'm really interested in getting feedback from you. Hopefully, you've been giving it to me all think long, but I'm really interested in feedback about how well this flipping the classroom worked with you guys. You hopefully it probably took you a little while to get used to it. Whether you liked it or didn't like it in the beginning, that may be different now. So, like I said, I'm really interested in hearing what you guys have to say about it, thinking if it's a good idea. I'm really, to be honest with you, I used you as a beta test for the class because I wanted to know, you guys are basically the population, a sample of the population that I wanted to use for my academy classes as well. So please be as blunt as you need to be as honest as you need to be. Just be constructive, not Ridley, you suck, you're terrible. So that's it. I'm going to present you guys with a problem. Think about this. Let's say that I've got a school, all right, and there are 1,000 kids in it, and we're going to have 1,000 kids. And this is it's a regular city school, and they publish something, and they claim that their attendance or their enrollment at the school is consistent with the ethnicity of the city that it's located in. Okay, so let's say, for example, that the city that they live in is 25% Hispanic. It's 40% white. Percent Caucasian. I'm going to put white. Sorry, not politically correct, but it is what it is. It's 15% Asian, and it is 20% black. 20% black. For those of you that are others, I don't mean to disrespect. Okay, keep it simple. Now think about this. I got a school of 1,000. How can I test this? Think about what we've done so far. Can I do paired data? What would I pair? Would I have to do pairwise across? You know what I mean? I mean, think about it this way. If in a school of 1,000, exactly 25% Hispanic would imply that I need 250 Hispanics in the school, 400 white people or white kids in the school, 150 Asians, and 200 blacks. But clearly, no school is going to play out like that. So what we're going to do is I'm going to introduce something called a chi-squared goodness of fit, and it's really easy to work with. Goodness of fit, and it's actually pretty fun. It's pretty cool. So chi-squared goodness of fit procedure, and I'm going to actually do this one with an example. We'll work through the example together, and then we'll be done with the section. Now, let's say that I go to this school, all right, and I'm going to have Hispanics, I'm going to have whites, I'm going to have I can give myself a little more room, can't I? There's only 4 of these guys. All right, I'm going to have, sorry about that, I'm going to have Hispanics, I'm going to have whites, I'm going to have Asians, I'm going to have blacks, and then what I'm going to have here, this is our race, and this is our frequency, okay? And let's say that I just go through the school, and I start tallying, all right? So let's see, in my school I've got 200 Hispanics, I've got 415 whites, I've got 175 Asians, and I've got 210 blacks. Now you may say, okay, well 200 Hispanics clearly is off. But again, hopefully in the back of your head you're thinking, well, how far off? It's definitely undervalued, right? The frequency is too small compared to the claim. 415 is too big. 175 is too big, and 210 is too big. It's as though these races gobbled up the extra 50, which is, I mean, theoretically exactly what they did. Now the question is, how can I test this kind of all at once? And it's actually really simple. It's very cool. It's a simple statistic called chi-squared, which we've used before. Remember when we did confidence intervals around standard deviations and variances? And if you remember how this guy worked, it was s squared and n minus 1 and all that good stuff. Well, we're not going to deal with that on this. This is a different chi-squared value. And all that it is it is the sum of the observed minus the expected, and we square it. And we divide it by the expected. All right, so O equals observed, and E equals expected. And you may ask, well, Ripley, what do you mean by expected? Well, expected. Well, check it out. It's real simple to figure out. I'll do this one in blue. If I could actually add a little column here. The expected values of this are, well, if it's 25% Hispanic and I've got 1,000 kids in the school, then 250 is the expected value that you would have, right? 40% white, there'd be 400. 15% Asian, there'd be 150, and then 200 black. So these are the expected values. Now, just like we did before, we're actually going to use a chi-squared table, but I'll show you how that works here in just a sec. Let's talk about the assumptions, just like always. So the assumptions are, one, always randomly selected. All right, so we've got these values which are randomly selected. Now, in this case, that's a little weird. All right, we're not actually taking a simple random sample. Think of it this way. What we're doing is the entire school is a school selected at random. And then we took all of the values and we did the demographics on that. So we got to fudge that just a little bit, okay? All right, number two is the data consists of frequencies. Data consists of frequencies. And by frequencies, that just means these guys. Okay, whoops, frequencies. They're these guys. So we're not going to write them as proportions. We're not going to write them as probabilities. Okay? Then last but not least, and probably the most important, is each cell is at least 5. All right? Now, you may say that feels very random. Each of the expected, sorry, I forgot to put expected. Each expected cell is at least 5. The problem is if they're not at least 5, then really very, very strange things can happen. Because if you think about it this way, in this case, this right here is, I mean, think about it. It's 80% of this. Let's say that this was a 1 or a 2. Let's make it a 1. And this were 10. All right? Think about what that would be. This would be 1,000% of what this would be. So if the numbers are less than 5, then you get these wild swings in variations. All right? Now, the only other thing that you need, this is the coolest part, other than the chart, the goodness, or the chi-squared chart, is you need to know what the degrees of freedom are, since chi-squared always deals with degrees of freedom. And it's simply the number of categories. In this case, that happens to be the races. Categories, sorry guys, it's getting a little late, -1. All right, standard issue. I think your book refers to this guy right here as K. I'm not sure. All right, now, watch how this works. All I'm going to do is, I'm going to rewrite my table. So I'm going to go 200, 415, 175, and you don't have to do it this way. This is just, for me, is the easiest way. So these are my observed. Then I'm going to do my expected, and this is 250, 400, 150, and 200. And then I'm going to do my observed minus expected. So I'm going to get -50, 15, 25, and 10. And then I might as well do observed minus my expected squared. That's -50, right? Sorry. So I've got 2,500. Let's see, 225, 625, 100, right? And then I might as, oops, that's my squared, by the way. And then I'm going to do my observed minus expected squared divided by expected. Okay? So 250, let's see, 2,500 divided by 250 is 10. I may have to do these guys right here. I've got quit. I'm going to do 225 divided by 400 is 0.5625, 625, 625. Whoa, sorry you guys. 625 divided by 150 is equal to 4.17. And then 100 divided by 20 is 5. So I know that chi-squared is simply the sum of all these guys. All right, so let's see if I can do this thing in my head. How good am I? I got 19.6.7325, right? 19.7325. That looks about right. Oh, if not, we'll just fake it. 96, yeah, that's right. So wait, 19, 755, that's it. Okay, now, just like before, watch how simple this is. I'm going to go jump onto my chart. Now remember, my degrees of freedom in this case there are 4 categories, so it's 4 minus 1, which is 3. I'm going to pop out. Here's my chi-squared right here. Now, watch how easy this is. Remember, we should probably pick an alpha level, but even though, watch how certain we can be. All right, first things first. If my degrees of freedom is 3, and I want my p-value to be 0.05, now really think about that. What we're saying is, if alpha equals 0.05, then my critical value for 3 degrees of freedom, just by looking at it, is 7.82. If alpha equals 0.01, then my critical value is equal to, what do we got, 11.35. Now, remember how this guy works. I'm going to pop this open one more time. Ah, that's too bad. Remember how this works. The way that the chi-squared looks, is it looks like that. So if I get far enough over, so if I pick alpha equals 0.05, then my critical value, let's see, what was it? What did that say again? 9 point something? 7.82. Then my critical value is 7.82. You know I'm going to have to change colors just because I love it so much. So this is my critical value. Well, in our case, my chi-squared was equal to, what was it, 19 point something? It was 19.7325. So chi-squared is 19.7325. Now we know that since chi-squared equals 19.7325 is in the critical region, we reject the null hypothesis. Whoa, but Ripley, wait a sec. You didn't mention what the null hypothesis is. Think about that. Let's write the null hypothesis just after having played with this. What do you think that the null hypothesis really is? What are we testing? Go back. We're testing to see if this distribution right here is close enough to this distribution. So what we're really testing, is whether or not, in our case, because we have 3 different deals, right? We're checking to see if the proportion in each one, not did I say 3, I meant 4, 4 different races or ethnicities. We're checking to see if they are all equal. Really? Now, you got to watch out for this equality here. In this case, I'm not really checking for equality, am I? I'm really checking to see if P1 is equal to 40% or 0.4. P2 is equal to, I forget what it was. Was it supposed to be 0.2? I forget. Let's look. It's 0.25, 0.4, 0.14, 0.15. So P1 is equal to, sorry about that, P1 is equal to I did it again, 0.25, 0.4. P3 is equal to 0.15, and then P4 is equal to 0.2. Now, traditionally, if we're looking for a uniform distribution, this is what we would write for our null hypothesis. However, we're starting to get pretty savvy, so I went ahead and jumped to the advanced move of checking to see if the distribution fits the claim. So that's another way that we could write up the null hypothesis if we wanted to. Now, there's a fancy way of writing the alternative. It's called at least one inequality, or ALOI, okay? Which means at least one of these values back here does not fit in the distribution. They could all miss. In fact, they all miss, don't they? But it appears as though, I would bet you that this guy right here, because it's a large proportion of what's supposed to be. Now, this guy, not so much, right? We're only off by 15 out of 400. That's not very big. That's what, 3.75%? This guy's off quite a bit too. This is 1 out of 7, right? So about 14% off. So those are probably the two that made it so that the data didn't fit the distribution. Okay? I don't know why I just stumbled over those words. All right? That's it. That's how it works. It's so easy. Basically, the general rule, and we're going to play with these in class, of course, is you're going to have observed, you're going to have expected, you're going to have it observed minus expected. It doesn't matter if you get the sign right on that because we square it, right? And then you're going to have an observed minus expected squared divided by expected. And then you just take the sum of them. If I take these guys, minus expected, and whoops, observed minus expected squared, that is equal to chi squared. And then all we have to do is take our degrees of freedom, and that equals k minus 1. And that's it. That's all there is to it. That's to check to see if a claimed distribution is actually descriptive of an observed distribution. Pardon me, too much caffeine again. All right, that's it. That's chi squared. We'll do some more in class. We'll putz around with it. Enjoy, man. This is your second to last lecture. We're going to jump into the next section here in just a minute. So enjoy and have a great day.